Hello class, this is theoretical models part 3 and it's a continuation of the fluid systems. The last time we were talking about the hydraulic resistance. Today we will talk about hydraulic capacitance. Hydraulic capacitance. Okay. Well, it is a term that used to describe the energy storage with a liquid, where it is stored in the form of potential energy. The general diagram to describe this model or system, well, we have a tank, and well, as we know, we have feeding, in this case the water. Normally the tank have a certain height capacity or design capacity, and we have outlet. Okay. Here, if we can rescue some of the variables very quickly, we have the height. Also we have in this case, the cross-sectional area, right? And we have the flow rate that coming in this case we can call it Q1, and the flow rate that coming out, in this case Q2. And also we can add variables, for example pressure 1 and pressure 2 can be the top and the bottom of the tank. Okay. So as we know, the height of a liquid in a container, or normally called a pressure head, is one form of such a storage. For such a capacitance, in this case, the rate of change of volume in the container. That in this case, how we can represent that the rate of change in volume is when the volume change over time. Okay. So this is equal mathematically to the difference within the volumetric rate. The volumetric rate means the flow rate at which the levels enter to the container, that we call it Q1, and the rate Q2 at which the liquid leaves. So saying that, we can approach to describe what happened in the container with the liquid. So we have Q1 minus Q2 equal to the difference in volume over time in the container. Okay. We know that the volume we can also identify it as area multiplied by the height of the liquid. So if we rearrange the expression here, we will have something like this: Q1 minus Q2 equal to the difference of the area, if we will change the area or remain constant, depends. The height, that it can vary, depends of the level of the liquid in the container, and the change in time. So this is equal to, if the area remain constant, that multiplying a differential of the height and over time. Okay. But the pressure difference in this case between the input and the output is pressure. Well, how we calculate pressure? So we know that pressure is equal to H or rho GH or H rho G. Okay, where rho is the density, as we know. Okay, and G is the gravity or the acceleration due to the gravity. And we have the height. Okay, so if we have that, what we have? So we have the flow rate 1 minus flow rate 2 is equal to the area that is multiplying the differential of pressure over rho G over time. Okay, this is equal to area of rho G differential of pressure over differential of time. If the liquid is assumed to be incompressible, well, in this case, its density does not change with pressure. So the hydraulic capacitance hydraulic capacitance, normally denominated by C capital, is defined as follows. So this is equal to the area over rho G. By saying that the difference of the volumetric rate is equal to C dP dt. Okay, if we will do integration of this equation, we can know what's the pressure in the container. So pressure is equal to 1 over hydraulic capacitance of the integral of Q1 minus Q2 dt. This is the theoretical model for hydraulic capacitance definition, means water in a container, and how based on the variables that we have in comparison with time, we will know the pressure in the system. We know that we can measure Q1 and Q2, and hydraulic capacitance, it need to be with the properties of the fluid, in this case the cross-sectional area of the container. By knowing this, if we would like to start to manipulate the variables, we will have a better management of the liquid in the container, or a better description of what is happening of the liquid in the container. Okay, see you next video. I hope you enjoyed this one.